The next topic is new challenges in numerical simulation of forming processes, multi-scale and multi-physics approaches. The speaker is Elisabeth Massoni from the Materials Forming Center at the Mines Paris Tech. Thank you.
Ladies and gentlemen, good morning. I would like to thank the organizer for the invitation, especially Stefano, to invite me to give this talk. It's a great challenge for me because it's a very technical talk. So with many equations, so it's very difficult. I'll try to do it in the best way. So here we have this title. So I hope this is okay. So CEMEF, it's one of the 18 research labs belonging to the engineering school École des Mines de Paris, belonging also to the Ministry of Industry. In that sense, we perform a lot of industry-oriented projects, and my lab is located, So my lab is located in the south of France, you know, in Sophie Antipolis. It's around 5 hours driving from here. So this laboratory is around 160 people with 60 permanent staff. Half of them are researchers, scientists, and the major peoples are, of course, PhD students, 17. So these young people do the real work in the lab. So I would like to draw this outline. So our business core is the material forming. But of course, we receive the material, we receive the part to be formed, but it's very important to know the origin of this part. What is the elaboration of this part? For example, the process, casting, solidification, and so on. After we form this part, but this is not the end of its life. After the part is, for example, assembly to a structure. So we have also to study the final property after forming in order to be sure that the forming process is okay. So it's the reason why I draw 3 parts. So thermal treatment, I don't know if it's okay, this one. So thermal treatment, so fluid structure interaction with a focus on level set approach is very technical, but very interesting way to solve this kind of problem. Then damage, fracture, but also void, closure. And we've finished with the grain growth stimulation. It's very important to stimulate the microstructure evolution in the finite element code, for example. And some concluding remarks. So first, for the thermal treatment, I present briefly the work performed by our scientist, is LIHM, and the base is the level set approach. So first, this is the first equation, sorry. So it's very easy to understand. So we work in immerse volume method. The idea is to use the same mesh for the part, for the environment, and for the frontier of the different parts. So this is very powerful. So the idea is to create a function in order to define the frontier between the different parts. So here it's easy, it's solids, air, and the interface between the two. But we can have also this board with the air, and we have to use exactly the same mesh for all, just to refine the interface between these solids and the liquids. So we compute the distance function between these parts and the other with the analyticals or NURB or different files. We sign this function with a level set function. It means that we define the function positive inside the solids, for example, negative outside, and null exactly at the interface. We applied anisotropic mesh in order to simulate the interface of the two parts. So you have here an example. So you have the mesh. It's exactly the same mesh, but we refine only the interface of the two parts. And we regularize, of course, the properties of the different materials. For example, here is elastic solids, and here it's a viscoelastic fluids. So we have to mix the properties of the different materials, like a very, very simple equation with the rule based on the mixture. So this is very simple, but it is the base of the approach. So just here some example. We treat the heat treatment in the oven, but also quenching for a very big part, thanks to the consortium on steel industry. And here it's a very good example. It means that here we have a very big oven in charge to heat a different part coming from forging industry. So it means that the half of this room. So we mesh all the part. We mesh also the closing and opening the door, the flame arriving, and also all the parts, the solid in charge to be heating. So in this example, we have the turning part in order to have a good distribution of the heat around the surface. And here some example of different geometry. We can have also this movie, this displacement of the part for this part here. It's for a very big part for the nuclear industry. And here it's more funny, it's for the brick. And it's also the same problem, is to have the good heating of the part in order to have a good distribution of the microstructure of the material. So this is for heat treatment. Now the application of this technique of level set in damage, fracture, and also void closure. So this work is performed by the team of Pierre-Olivier Bouchard in the lab. So here, an example of simulation of crack, and also here during forging, and also the same simulation during extrusion. We can have, of course, in the macro scale, the simulation of this failure, but it's very important to understand what is the origin of the failure and what is the final properties of the material with this or without this kind of failure. Because we can have some voids, and after we can have the closure of the void, it is important for the final part or not. So in order to be precise with this simulation, it's very important to predict this damage at different scale, especially at micro scale. So you can see here, so it's not so easy without mouse. So you can see here different images of this kind of failure. Here is with the equation, and here it's with failure at different plane. So we try to use this kind of level set approach in order to be able to simulate this. So another question. Here, very simple. We have different domains, like my board and the hair, but here we have the inclusion of inside the material, the matrix, and we have the void. So we define different level set function in order to be able to define the different interface between the three material. So here, one level set function defining the void, the difference between matrix and void, another void and inclusion, and so on. So it means that we have three domains to be defined and three level set functions. For the mechanical properties, we have also to be able to simulate the real properties of the material. For example, it's elasto-viscoplastic material for the matrix and the inclusion, and another properties for the void. And each domain has its own mechanical properties, and we have to mix the properties of this material, global material, using a mixed rule. So here we have here the void and here the matrix. So using this, we try to refine the interface between the inclusion, for example, and the matrix. We have a small thickness, and we have to define this thickness in terms of finite element simulation. So we define this using a matrix based on the level set function. I remind you it's 0 at the interface. But we can use also an error estimators, a priori error estimators on the mechanical properties. So here we can have, the previous one, please. Sorry about that. So here you can have anisotropic distribution of the elements around the interface. So this is classical one based on the interface. But we can have also the metric mixing the mechanical properties and the zero value of the interface. So this is very interesting and important for the simulation. For example, here it's the finite element mesh of matrix here, inclusion here, and here we have the interface between the matrix and the inclusion based only on the level set function. If we adapt the matrix with also the mechanical properties, we can have this kind of meshes. It's quite different. So refinement, for example, here, and we have here a very fine mesh. This is also very important when we have matrix inclusion, but also void here. So matrix inclusion on void, because this is also the real life of the material. There is sometimes voids. The voids increase or decrease. It's very important to be able to simulate this one. So how the operation of this void, is the nucleation, the very beginning. So you imagine that we have here a void, a matrix, and here is just a criterion based on the normal stress. And when we achieve and we reach this threshold, we have the nucleation of a new germ here. So we can see here this, this new void appearing here. This is one of methods. It's only interface debonding. The other is the fragmentation. So the fragmentation, we have this kind of inclusion here. So remember, this is the image here. We have the inclusion here, the matrix, and we are applied a stress. And when the stress got this threshold, is the maximum principal stress, we have this failure on a specific plane. So I suppose, so normally, yes, thank you. So here, you can see here an animation on the finite element simulation of this second method. It's very important for you, it's not visible, but all is the same mesh, so even the void in gray is meshed. So there is the evolution of this void due to the, for example, during a tensile test, and we have here the debonding here on the part. Okay, so another example is here with the two methods. So we applied a tensile test on the sample with some inclusion, and we have the different behavior of the material. So it's very important to notice that the gray part is also a mesh. So everything is meshed. So it's the same mesh. We just refine the interface of the different parts. So you can see here the interface of the inclusion and the matrix, and here the void appearing, and the void is also meshed. Okay? And here it's very interesting. It's the nucleation, the growing, the growth and the coalescence of this void. So here a real image, and here the finite element simulation of this using this level set approach. So this is very interesting. We have the growing of this void, so you notice that it's not really a spherical part, it's really a 3D simulation with a coalescence of the two. So there is more details on the poster given by the young PhD student, Modessa. It's pub. Okay, so this is the end for the damage failure. The last example is how to simulate the grain growth and the microstructure evolution using exactly the same approach. This development is done with the supervision of Marc Bernacchi. So, the microstructure. It's very important to be able to simulate the microstructure evolution during forming, but also during heat treatment, because sometimes there is a different and strange things appearing, and the industrial people, especially people working in aeronautics with super alloys, are very interesting to understand what is the origin of this strange growth of grain and why in some parts there is a very large grain and other part very small grain. And the question, is it important to have a small grain, or it's not very important to keep this very large grain? So it's important to be able to simulate this evolution of microstructure in real operating condition, or the closest operating condition than in the real life. So we discretize the part with a different grain, and we can also have a small particle inside the classical grain in order to see the influence of this second first particle in the microstructure evolution. So the evolution of the grain is based on the very simple kinematics equation here, the velocity. Here you have the boundary mobility. Here you have the term with in terms of curvature of the grain, in which we can have boundary energy, grain size, and Zener pinning. This is a metallurgical keyword. And here we have the store energy, and here is the external normal at the surface of the grain. Just to say you that this equation respects the grain size distribution, the second phase fraction, and morphology. It's very important also. Take into account the capillarity effect. It's important to have the evolution of this grain size, the store energy, and deal with Zener pinning. I don't see if I have time to speak about this. So here it's exactly the same discretization than the previous one, but at the very small scale, at the scale of the grain. So we have the discretization of this grain and the definition of the interface of this grain with the others. So we define the level set function. So this level set function is positive inside the grain, null between the grain and other grain, and negative outside. And with this discretization, we are able to follow the evolution of this finite element mesh. Here, it's the same mesh, which just defined the interface between grain and other grain thanks to the level set function. So we can here apply the evolution of the equation of the movement of the grain, and we can move and have this simulation of the evolution of the microstructure. You can notice here a very fine mesh between the different grain. Okay, this is very important. Just I finished with this one. Sorry about that. It's also very important to have a real image of the microstructure and after to pass on this microstructure a finite element mesh. So here we have a real image. We treat in different way this image, and if we see this red square, we have here the image of the finite element corresponding to this one. So this is very important in order to see the evolution of strange phenomenon like second phase particle during the simulation. So I don't have time, I know. And this equation, so it's not really. So here we can see the evolution of these meshes during operating condition. So we can apply a thermal cycle. We can apply also a stress, a pressure, and or strain on the boundary as a boundary condition. And we have the evolution of the grains. So you can see that some grains are decreasing in terms of size, and the others are increasing. And here, I think I finished with this, is the growth, strange abnormal growth of grain in superalloys. And here we have all the data for this simulation. And we have a very strange things, and if you want to have more details, you can go to discuss with Benjamin Chaltès in front of the poster 5. Okay, concluding remarks. Of course, our business core is the material forming simulation, but we need to know the origin of our material, and we have to know what is the use of the formed part after. So we have to work on elaboration, for example, casting, solidification, on forming, including microstructure evolution, heat treatment, heating, induction, heating, quenching, joining, welding, assembly, of course, but also in use properties like damage, failures, and the life of the void. So we developed the finite element simulation based on the P1 plus P1 elements, tetrahedron elements. So this is very important because all our remeshing algorithms are based on this kind of element. So we don't have another elements in our library. We work on immersed domain using this level set interface. It's very interesting for us in order to represent the moving interface in solids, in fluids, and also in fluids structure interaction. But now the challenge is to reduce the computational time and also to decrease the space of this simulation. And we work a lot on this. Thank you very much for your attention.